Hello community, so great that you are back. Today we talk about the impossible mathematics and how AI can solve it. Now, we have every year the International Mathematical Olympiad, and in 2025 it was at the Sunshine Coast in Australia. And a lot of young people here, you have to be under 20 years old, participated and were greeted here by the inhabitants here of the island, and it was simply amazing. But you know what? Also 3 AI companies decided to participate. One absolutely official, one not at all officially, and one was a surprise. Let's have a look at this. So here you have the statement of IMO president here and said, hey, we can confirm the Google DeepMind has reached the much desired milestone, a gold medal score, astonishing in many aspects, graded, clear, precise, and most of them easy to follow explanation. Officially here, Google DeepMind gold medal. Now, on a technical level, it is interesting to see that Google switched from a formal mathematics construct to an informal mathematics construct. So it went here from a translation of problems from a natural language, as given by IMO, into domain-specific languages, and it chose Lean 4. So Google said, hey, it took us 2 to 3 days just for the computation in 2024. But now in 2025, they achieved a gold medal. Because they said our Gemini model is now operated end-to-end in natural language, and we competed here within the normal 4.5-hour computation time limit. Great. But they also said Gemini is now trained on a novel reinforcement learning and on a theorem-proving data stream in the pre-training. So fascinating. So they have now 2 options. They say, well, we approach this year. Well, this was based on a natural language, it's Gemini. They also continue here to make progress on the formal language system that they used, like Lean 4, for their LLM. It's called Alpha Geometry and Alpha Proof. And Google says, we believe agents that combine natural language fluency with rigorous reasoning in formal languages, like, Lean 4, will become invaluable tools for mathematics, science, engineer, research, and everything. Absolutely fascinating. So if you're not familiar with Alpha Proof, here a short summary for you. Now, we talked about Lean 4 in the context of DSPy 3 in one of my last videos. But as always, we have the option to have an LLM, and this LLM has a tool use as an agent, the memory. So therefore, the tool use could be Lean 4. And guess what? We have a beautiful reinforcement learning that we also can do in parallel during inference time. Or there's another option. So if you are Google, if you have 100,000 GPUs, no problem. You say now, hey, wait a minute, we have an LLM. And now we have not, if you want, normal English linguistic, but we have now a formal language, like a Lean 4 computer language. Now, guess what? The LLM doesn't care if it learns here a linguistic pattern or a formal language Lean 4 pattern. So they created a huge data set of Lean 4 solution-proof theorems and everything, and they used it then to train here this LLM on abstract reasoning or proof primitives. Absolutely fascinating if you think that in this video just 2 weeks ago from University of Princeton, I showed you their super intelligent also builds on symbolic logical primitives, but Princeton did deduct their logical primitives from a knowledge graph for specific tasks. Google now makes a much more general approach. If you want to learn more about Alpha Geometry 2, I would highly recommend this paper. But as I told you, there was an unofficial participant who did not trust its own system enough to officially participate. An AI company you do know. So let's talk about here the second unofficial participant, apart from the 630 human students. And I can tell you now the results are published here. 11% of them achieved the gold medal. So young mathematicians here, younger than 20 years old, 11%, this means 67 contestants have a gold medal. And now one company, and I used here ChatGPT for my search algorithm, and I said, hey, has OPENai officially entered the IMO 2025 competition in Australia? And ChatGPT from OpenAI tells me, no, OpenAI did not officially enter IMO 25. OpenAI, by contrast, because Google DeepMind formally participated and cooperated with IMO organizers, and the result of Google was officially graded and certified by the IMO judges, OpenAI decided to do something else. OpenAI, by contrast, tells me ChatGPT, evaluated its model performance internally using some former human medalists. So they get paid by OpenAI. So OpenAI selected specific specialists that had received a gold medal in the past. OpenAI, of course, it's an American business model, pays those specialists for their services. They now evaluate this internally, and then OpenAI officially declared it also achieved a gold medal. But OpenAI did not submit anything through the formal IMO process and was not part of the official competition entry list. So when I read this, validated by ChatGPT, so let me summarize. Google DeepMind, yes, officially entered, and Google DeepMind Performant was certified by the IMO committee. OpenAI did not officially enter, they had not enough trust in their own system, and they did not went through the official processes, but they self-graded here their own performance when they hired former IMO medalist. And then OpenAI declared itself the winner of a gold medal, and before everybody else, because it seems that they did not respect the deadline for the publication of the results. This is a company that is so eager to be here in the news, in social media, that somehow, for all the 630 students, this company showed a behavior that is not recommended. But let's talk about the other company I found out today. Guess what? We had another competitor from a global AI corporation, and you guessed it, China, ByteDance Seed. Now, I don't know if you're familiar with their model. They have a Seed 1.5 thinking model. They call here it themselves an advanced, superb reasoning model with reinforcement learning. Yes, beautifully, great. You can find here everything from ByteDance here also on Hugging Face. Just 4 days ago, they have here new ideas and new models. But they published here, just yesterday for me, July 31st, 2025, Seed Prover, a deep and broad reasoning for automated theorem proving. And this is now the main paper of this video. And you might say, hey, wait, Google also had here a prover that works also here, was fine-tuned here on theorem proving. And today we learn, guess what, China's ByteDance has also now the Theorem Prover, and now it's not called Alpha Prover, but now it's called Seed Prover because their model is called Seed. Okay, great. However, this is now a very interesting paper, and they are very open about how they train it. They have also, as you see, a Seed Prover LLM and a Seed Geometry LLM, exactly like Google has here also the Geometry 2, Alpha Geometry 2, and the Alpha Prover. So a very similar approach that China tells us now, hey, we can do this. Now there are a lot of different benchmarks, but as you can see, 100% here's top line, and Seed Prover now saturates this test and achieves close to 100%. You see here DeepSeek Prover version 2, I had a video on DeepSeek Prover version 2, was still below 90%, but now, just months later, we are now at 100%. So we need something new. And now here, the Chinese also say, following here this, if you want to call behavior by OpenAI, they also now self-claim they successfully proved 5 out of 6 problems in IMO 2025. So they also achieved, and this is now my interpretation, the gold medal. Exactly like OpenAI self-declared the gold medal. Now, ByteDance was officially invited, as I learned here, which I'm not sure that OpenAI was officially invited. But also ByteDance says, but yeah, one of our approved finished after the deadline. So I would say these 2 gold medals that were not officially rewarded by the committee of IMO 2025, you should know a little bit of the backstory. But let's talk about the technology. ByteDance said, the core idea here is explore the problem, generate, improve smaller, manageable, intermediate steps, reduce the complexity into lower complexity lemmas for mathematical proofs, and then use these proven lemmas as, if you want, primitives, as building blocks to construct the final proof. So you see, it's always the same idea. There's no new idea in the whole field of AI. Reduce complexity, go to primitive building blocks, and then build it. Now, they said we design now a 3-tiered inference strategy for the budget. This is now interesting. So let's have a look at this. Yeah, if you're not familiar, what is lemma-style mathematics? Just a reminder for you. Now, they said, this lemma style is not interesting because let's also solve another problem that we have, and this is continuous learning. So if we have those lemmas, and they are proven here by Lean 4 compilers, let's build a lemma pool. And this lemma pool represents now a form of persistent, verifiable, with the compiler, knowledge primitives. So the model is not just generating a text, it is building now a library of trusted tools. This means lemmas. So it's not a tool with an API call, but it's more like a tool, like a software package you can use that is mathematically proven to be working, and we can reuse this for different attempts. So what it achieved with this idea to accumulate and compound knowledge here on the mathematical level. And they continued here because they build a neuro-symbolic synergy, no? So they say the LLM, this is, you want, our neural network part, excels here at proposing creative and intuitive steps, while our, if you want, symbolic part, the Lean 4, the compiler, provides here immediate verification. So you have here a very strong feedback loop, and now take a step back, have a look at this as reinforcement learning, and you see immediately that Lean 4 compiler is now our reward model, and this is simply a reinforcement learning exercise. But remember, we accumulate here mathematical lemmas. And then they say, to optimize here the inference strategy, because remember, you would only have 4.5 hours, no? We have to optimize this. We can't just run it for days and weeks, no? So they say we have now a 3-tiered inference strategy, light, medium, and heavy. And what we want to achieve, as always, a trade-off in reinforcement learning, the width of your solution and the depth of your solution. So we again are faced with exploration and exploitation optimization. Now here let's have a look at the light inference setting. So you see, we have our first whole proof, and then we just check it with a Lean compiler. If you see here the red X, it's not working. So self-summary, what happened? What was the error message I get back from Lean 4? Maybe start to write another version here, another prompt for the proof. Put it again here in my Lean compiler. No? Okay, you get the error message back. You have memory. So write an optimized self-summary. Try to self-correct yourself. And then you do, and then somehow, if you have your Lean compiler tells you, hey, yeah, this is the correct one, you have your solution. It's a little bit more challenging if you go to the medium inference setting. You know why? It is built on a modular basis. So if the Lean compiler tells you, hey, this is what you showed me, the prompt is not working, you use now the light inference schema that we just went through for each particular lemma. Then you have a problem with a new context. You go through this again. You have an inner refinement step until you have a go from your compiler. So you see, they build here the complexity on the shoulders of the other method. Of course, for the real interesting problems like here in IMO 25, they have to rely on the heavy inference setting. But guess what? Since it's a modular approach, you immediately understand it. So we have different conjectures, and I show you this in an example in 2 minutes. And then we try to find solution with a light inference. No, we don't want to waste time. We don't want to waste energy. Maybe it works, maybe not. If we encounter a problem, we go to the medium inference methodology. And we run through all this and they tell us, well, we can go up to 5,000 conjectures. And I will show you an example. And then you just run through all the possibilities. This seed proven, let's talk about this, is a very, very kind of a generalist with a very particular strategy. So at first notice that it's trained to break down the problem, the complexity, break it down into independent, reusable lemmas first in Lean 4. Reduce the complexity. And this here is in Lean 4, for example, easy piece of code. You immediately see it. So modular approach, what you achieve, progress tracking, modularity, reusability, inspiration. A correct proof of a lemma can provide clues for providing other lemmas. Absolutely great if you have this then in your pool. Let's go a little bit more in detail on the light inference. Now, I told you I'm going to show you some examples, so here we are. What is the overall goal of the light inference? Solve simple problems and fix some syntactic or minor reasoning errors immediately. What we do, we have a simple refinement loop. So the language model generates here a proof attempt in Lean 4. This code is now passed to the Lean 4 compiler. It is run, and if it fails, guess what? The compiler tells you, sorry, error, but it provides a feedback what went wrong. So the LLM receives this problem, its failed attempt, and the Lean 4 error message as an input, and along with a self-summarization of the failure. So it tries to understand what went wrong and then generates here the next, hopefully now the correct attempt to write here a Lean 4 proof. You can have this loop for, we define 8 to 16 iterations, and you immediately see this is only for very light complexities. Now, if you go for a medium inference or deep dive, you have to solve complex problems that require breaking down into more complex subproblems. So you have a nested refinement process. Let's have a look at this. You have an outer refinement loop and an inner refinement loop, and guess what? It is a light loop. So the outer refinement loop, like the light settings, works on the main theorem. So if this loop generates a useful lemma, but fails to prove it, it spawns an inner refinement loop, another full light inference process with its own dedicated budget, tasked only with proving that one difficult lemma. And if the inner loop succeeds, now the proven lemma is fed back to the outer loop, which can continue its work on the main proof. So you see, you go down in the complexity, you divide it up, you come back, you have now the full complexity again. Easy. Now it's really interesting to look at the heavy inference structure. No? This is where you tackle the hardest problems where the proof path is completely unknown. And now just think about it. What you want to do if the path forward is unknown? You have to be inventive. No? You say, hey, I need to check out 100 or 1,000 ideas, and maybe one of those ideas will be the path forward. And this is exactly what the AI does. So we have here a conjecture, and we generate now. And so instead of trying to prove anything, the model is first prompted to generate thousands of potential useful ideas, conjectures here, related to the particular problem that I've given the machine. So if you want, it explores here the problem space in a very wide way. Then we have a filtering. Now the system uses here the efficient light inference, guess what, modular approach, and try and automatically prove or disprove each of those thousands of conjectures. Here you see parallelization is paramount. Then we have the lemma pool population. All the successful proven conjectures from the thousands and thousands of conjectures become now trusted lemmas. They have now a particular tag right next to it, and you said, this you can trust. I validated this particular mathematical proof. And they are now added to the problem's lemma pool. So you see the system builds here, just trying out some crazy ideas, thousands and thousands of ideas. It builds, if you want, a ladder to the next level. And then the final synthesis after days of thinking, and really they write about days of thinking, because you have to generate this pool, no? The system will have accumulated hundreds and thousands of non-trivial, proven facts in the mathematical lemmas. It then selects the most promising lemmas, different ways how you can judge this, and uses now the medium inference setting to weave them into a final proof of the main theorem. So you see, it's a loop that is within a loop, and it's a modular approach. It is simple, but you have to come to this idea, and you have to have the guts to tell the machine, just generate 5,000 conjectures. Just try it out. Maybe you'll find one that is working. Now, I told you that Google 2024 did have human intervention in the translation of the natural language prompt into the formal language Lean 4 prompt. And now I was very interested, what about ByteDance? And they tell us here under the IMO 2025 heading, the human translation, their AI does not read the natural language mathematical problem from the exam paper. Instead, all problems were translated into the formal language statements by human experts. So here in this particular slice, ByteDance is now where Google was with 2024. They had to have human experts. Remember, Google 2025 already switched the system to the next step of pure natural language processing. So this expert now converted the English problem into a precise theorem statement in Lean 4. And of course, the better the humans performed, the better or the easier the AI had in solving this. And they tell us, hey, this is a critical step as natural language understanding is still a major challenge for the ByteDance implementation. But they can do this now where Google was just less than a year ago. And then we have the AI proving. So once the problem is formalized now in Lean 4, the seed prover and the seed geometry system takes over, like with Google. They use the vast computational resources and the methods described in the preprint, lemma generation, inference, to produce now the formal proof. This proof is a complete verifiable block of Lean 4 code, and we have a Lean 4 compiler, so we have easy a reward system, a verification, and you know how we continue. So both seed prover and seed geometry are powered by LLMs, and these LLMs were specifically and intensively trained on the Lean 4 data, on the Lean 4 proofs, and on the compiler interactions. So again, where are we? We are just here in reinforcement learning, if you want, with a perfect critique LLM. But now it's not a critique LLM, now it is a Lean 4 compiler. It is a formal language compiler, so we get here a binary reward signal, yes or no. Yeah, action, reward, provide crystal clear, unambiguous training signal that is used to update the weight. Great. Extrinsic RL. And I thought, so wait a minute, are they already at the step where Google is this year that Lean 4 is now kind of integrated in the pre-training data and it has inherently learned the logic of Lean 4 completely? Or do they still use Lean 4 as a tool if they have the inference run? And now reading the paper, just have a look here at the workflow here in this, you see at every step they have here the Lean compiler as the generator of the reward signal. And if Lean 4 compiler says, hey, this is a red X, this is a failure, you see they have it here as, let's say it, a tool. So what is now, I ask myself, the real delta from ByteDance now, just published today, to what Google did in 2024? Now, what I really think is interesting is they have this 3-tier strategy approach. Solve immediately what's solvable with the slight scenario with bug fixing. Then, the next step of the complexity, the medium problems, the deep dive here on the lemmas I showed you. And then for heavy, we have really to go into exploratory conjecture generation when the path is absolutely unknown. There's nothing in the training data. There's nothing available anywhere. This is a so brand new virgin problem that nobody knows about it. Nothing is available. So now you have to be creative as an AI. This system automatically creates a self-learning lemma pool on a mathematical level. So a persistent growing database is maybe the wrong word, growing knowledge base of proven facts for a very specific problem we can input into the Lean 4 compiler and get here green light or not. So if you want, ByteDance has here this approach of a kind of a strategic thinker implemented here in this block version. So sketches out a plan, proposing here the conjectures, proves the necessary side results or the lower complexity lemmas, and only then starts to assemble the final argument. So if you want the seed prover, now in my simple interpretation, and please, if I'm wrong, leave something in the comment, this seed prover now adds a strategic layer on top of the loop, no? Because it doesn't just ask, hey, what's the next line of code? It asks the next level question. Is this problem simple enough to solve it directly? Light inference. I'm stuck on this one lemma. Let's focus all the energy on solving just that, medium inference. Or I have no idea what to do, heavy inference. So here, if you want, you kind of zoom out and you try to manage and create and design intermediate goals in a very specific way. So you have your proven lemmas and your not proven conjectures. And how you dynamically allocate now your computational resources, this is, I think, where seed prover is really special. And remember, this is the first day I read about seed prover. I have no other information, only the documentation by ByteDance itself. So this is here my very first understanding. Yeah, for conjecture, just wanted to give you some additional information. I see a conjecture as an unproven mathematical statement. It's, if you want to guess, a hypothesis, anything else, but it is helpful. It is maybe a step forward. So its purpose is to map out here the complete huge problem space. And those conjectures are like arrows you shoot in the dark, or you have a flashlight and you point in all the direction in a room. So you want to generate or find as many possible paths forward in the reasoning sequence without really committing to one. And they write here the authors, the system generates a vast number, by default 5,000 conjectures, to ensure it covers here the interesting properties of the problem. So you really make sure that the complete solution space is more or less covered with at least here a vector bundle, or if you want, you flashes the flashlight here, the beam of light into the corners. Just think about it. Conjecture 1 might be, you've given me a problem, no? And then conjecture 1 might be, the LLM says, hey, perhaps the function f is always positive. Or the function is always negative. Or the function is fluctuating between positive and negative. Or, whatever can be a conjecture 2548. I bet this triangle APC has a particular form, shape, or has a particular symmetry. Those are just thousands and thousands of ideas floating here in this giant conjecture pool. And then we come to the filtering phase, no? The system then uses its efficient light inference setting as a rapid-fire proof attempt engine. It takes each conjecture one by one and tries to prove it. Fails, success, success, great. And therefore, with the positive samples, you populate your lemma proof, your trusted lemma proof. And after days of this process, you have a lemma pool that contains hundreds or thousands of non-trivial, proven logical constructs. And now the system switches gears, né? Now it uses here the medium inference setting, and we just talked about this. And then you go for the heavy inference setting. But I think now we have the building blocks to understand here what our colleagues in China did. Very interesting. Plus, in addition, I would like to mention that they built their own high-performance interface to Lean 4. They called it Liu Kang, a custom high-concurrency Python interface. Interesting. Plus, for the geometry engine, and we not talked about it, but you guess what it is, they rewrote the symbolic deduction engine for seed geometry from Python into C++. And their C++ implementation gave them a 100-fold speed increase. Amazing. Self-summarization for the error correction. So you don't just get the error message back, but the prompt includes now a self analysis, a self-summarization of the previous attempt from different perspectives. If you want a form of a metacognition, forcing the model to reflect on why this particular path of a solution failed, hopefully leading to more intelligent subsequent attempts. And finally, an LLM judge for dilemma selection. Dilemmas are ranked not just by their proof difficulty, but also by their semantic relevance. And of course, you know how the semantic relevance is always judged by another huge LLM. So interesting, you have so many LLMs in the pipeline and their interdependencies, and they managed to get so many problems of IMO 2025 correct. This shows us that it is really sophisticated pipelines where the LLMs are not just used for generator, but also as evaluator, also as curators, as idea giver within the complete, much complex reasoning process now. So, interesting. This was just a very short journey here to the International Mathematics Olympiad 2025 that you see what are the global corporations working at. What if they say money? I don't care about money. I don't care about 10,000 or 100,000 GPU configurations. I just want to solve a problem with the maximum power that I can have on this planet. And 3 companies kind of succeeded. 1 officially, this is Google with their Gemini model, and 2 self-declared that they had this performance. 1 was OPENai in the US and the other one was ByteDance in China. Very interesting to see here the leading and bleeding edge of AI research. I hope you enjoyed it. Have a look at the paper. And if you subscribe, I see you in the next video.